Hello and welcome to the course. I'm your host today, Lee, and I'm speaking with Professor Tiffany Shaw from the Department of the Geophysical Sciences. She's a climate scientist who studies the physics of the atmosphere and climate change. Professor Shaw is here to talk to us about her career path and how she became a University of Chicago professor. So, Tiffany, this is a big question, but can you give me a sense of your career path beginning in your undergraduate years to becoming a professor at the University of Chicago?
Sure. In my undergraduate years, I was very interested in aspects of physical science and started out as a major in math, taking also physics classes, and slowly over time realized that, applying some of those tools to esoteric problems was not motivating me enough. And thankfully, during my undergrad, I was put in touch through a math professor with a professor in the Department of Earth Science at my undergraduate alma mater. And they suggested a course that was very mathematical, but applied to the Earth. And in specific terms, this is the study of Earth's atmosphere as a fluid and representing it using mathematical equations for the conservation laws of, energy and momentum and mass. And through that happenstance of those, wonderful professors who made those connections with me, I took a class and ultimately realized that this is what I wanted to do. I realized that I wanted to use the tools of physics and math because they are recognizing how powerful they are, but I wanted to apply them to a problem that of things that I could see, that I could explain, so that that I felt. So that was certainly one of the motivations for turning my attention to climate science, to the atmosphere, to the physics of those things. But on the other hand, I was also growing up in a family who were avid pilots. And so I had also that experience, really privilege of being able to fly airplanes and, be within the atmosphere. So somehow it all kind of gelled really quickly once I found that particular course. And thankfully, having been connected to that professor who taught that course, I did an undergraduate research experience with her, and that really further solidified my interest. I also did some undergraduate experience in more hands-on things like helping to operate a radar and collecting data from a radar. And I think it was through those different research experiences that I, continued to come back to the sort of the math and the physics of the problem. And it really, I think, shaped what I ended up wanting to do after my undergraduate degree. But to be honest, I never really had that epiphany that, I not only do I want to do this, I also want to be a professor that does this research. So it was definitely a learning process through experience, being able to conduct research in the summer. That really made it clear that this was a possibility. And then my last year of undergrad, I did a research experience with a professor who would subsequently be my thesis advisor, and really had a wonderful time. He at the time had a very large group of postdocs and PhD students building a climate model for the atmosphere and thinking about the ozone hole and so on. And it was such a welcoming environment to be a part of a team who were looking at these different aspects. And while my undergraduate project was a very small part of it, I had the support of all these people around me. And it also, made it clear that Earth science or this type of science was very collaborative, which, in some other disciplines, it's not. And so that was, I think, another real turning point. And so having completed my undergrad, I realized I wanted to continue to at least, do a graduate degree. I should say my family background didn't have anyone who had pursued higher education in that form. They'd all gone to college, but they had pursued higher education. So that was an interesting conversation, but I was thankful to have the support of my family and fellowships to continue to pursue my education as in terms of a master's and a PhD. And yeah, my PhD experience was, I think, like most are, there's a great thing called PhD comics that I always point graduate students to that kind of gives you the full picture of what it means to take 5 years of your life, in North America in particular. It's shorter in Europe and some other countries, to, pursue research, and how it's at the beginning, very exciting, and you got all these ideas and you have a plan and you pass your qualifying exam, and you're, very bright eyed. And then, year 3, it's definitely some things have worked out in the plan and many things haven't, which is, in some sense, just a microcosm of doing science in general. I think that's in some sense the beauty of it, the challenges that it presents. It's not always a linear path, but I was thankful to have a very supportive advisor in the freedom to start working on a problem that had many different approaches. So I had a part that I was doing, very detailed math to solve equations and to reveal underlying relationships and constraints that the atmosphere needed to satisfy, and then translate those constraints into some practical, quantifiable impact. So why do we care that momentum is conserved in a certain setup? And it has these really, I was able to show within the context of my PhD that conserving momentum for the smallest waves in the atmosphere has a really important impact on the surface climate. So not just in the atmosphere above, but, the pressure at the surface and the winds at the surface. So it was a very, I think, gratifying experience to be able to tie different dots together, going along. And I have to admit, during my PhD, I was very much heavily engaged and head down, really interested, focused. There were problems trying to get through them, relying on my PhD colleagues and postdocs. And it all kind of happened really quickly. The next step, I would say, I was fortunate enough to be able to go to conferences and interact with scientists outside of my university. And it was through those interactions that I was encouraged to apply for opportunities, not only for postdoctoral fellowships, and I did that and got one, but then after having accepted that, also being offered faculty positions at quite an early stage. And it was definitely overwhelming. I didn't have, as I said, a lot of family to rely on in those decision-making moments. But what I did have, which, I always will be thankful for, is a good mentor in my PhD advisor, helping me navigate what the next steps involved and just providing that guidance that is really crucial. So in some sense, it was a lot of kind of just following a path and maybe not having a big vision. I never thought at any point in my career, like, I'm going for this goal. My goal is to be a professor. It definitely was something that I came across and I'm very thankful for, because it's given me an incredible amount of flexibility and just joy to be able to pursue science as a career. And so that's sort of, I guess, how I started my first position. I wanted to also mention, though, that my trajectory after that was a little more complicated than maybe others have experienced, in part because while I had accepted a position to be an assistant professor, my significant other was still pursuing his PhD. And so while I was getting myself established as a new professor, there was this looming issue of what we call in academia the two-body problem. Namely, my partner and I at the time, we were not living in the same city, and that creates a whole level of social emotional issues, not only financial, but emotional, to try to carve out the time to be together. And that took a number of years to solidify. So I arrived at the University of Chicago in 2015 as a consequence of solving the two-body problem. My husband is a professor at Loyola University of Chicago, and it wasn't, an easy path to solve that. But I did, as always, rely on colleagues who had gone through it and who didn't have any magical powers to, help me solve it, but provided, in a very detailed way, their experience and what sort of factors they needed to, consider when they look back on how they were able to solve the two-body problem. So I think the two-body problem is really one of the major issues in academia. But thankfully, as I said, we have managed to solve it and are now happily settled here in Chicago.
So in the simplest terms, Tiffany, how would you explain what you currently study? And you can explain it like, I don't know, like I'm a 12-year-old or a 14-year-old.
I'm a climate scientist. And what the climate is, of course, is the patterns of rainfall and temperature and winds that we experience on Earth that, of course, vary with the seasons. So if we're away from the equator, we know that in the summer it will be warmer than in the winter. And so I study the physics and the underlying mathematics that represents that physics of what shapes the climate. Why do we see the climate? How do we understand the climate as it is? Of course, we know winter is colder than summer because of the sun, but there's a lot of variation amongst day-to-day weather and and how that shapes climate through the chaotic nature of the atmosphere. So I'm very interested in why the jet streams are located in certain places, why the hemispheres have differences. So why is the northern hemisphere jet stream different than the southern hemisphere jet stream? And one reason to think about these big picture questions is because we are currently, of course, undergoing an experiment of climate change through the anthropogenic emissions of carbon dioxide. So the burning of fossil fuels has now is perturbing our climate, and understanding how that perturbation will manifest. So how will the rainfall patterns change? How will the jet stream patterns change? How will these climate patterns change as a consequence of our actions? Is one of the most important questions facing society today. As a scientist, as a physical scientist, the tools that I bring to bear to understand what's happening and what will happen in the future is physics. So physics, of course, encapsulates our understanding of the world, and it gives us a tool through that understanding of predicting changes. If we make a certain change, what is the consequence? And so in my research, what I do is examine these constraints from physics, conservation of energy, conservation of water, conservation of momentum, and how they can be brought to bear on this problem of climate change to reveal the impacts of what's going to happen, where, when, and why, so that society essentially can better prepare. So this is a very, of course, interesting area. I obviously often get asked if I am depressed about it because, climate change is manifesting impacts that are extremely serious and will have important, consequences from all across all dimensions of society, and really requires society to get together to understand and mitigate those impacts. But we can't mitigate or plan around it without the science, without the information, because we need to be confident in what's coming and how our actions, can change what's coming, and obviously then, make decisions based on ideally, sound scientific reasoning and information. And so that's sort of where I feel my piece, where I come into this bigger picture that, if someone is trying to plan in the future, they want to know how will the rainfall patterns change. And we attack this problem just like any physicist does, stripping away the very complexity of the problem and taking it one step at a time. So there's a great analogy, physicists will they'll tell you to think about a spherical cow. Of course, a cow is not spherical, but we start with kind of stripping away some of the complexity to reveal the underlying simplicity. And so through this approach, we know that what regions will get wetter, and that's tied to very sound physical, reasoning, that moist regions will also get moister. And my research has shown that as a consequence of these, really well understood effects, we will start to see manifestations in the jet stream. The jet stream should shift poleward. And we think it's tied to these behaviors of the moisture. And then I'm also looking at how storms will change. So it's kind of, multiple layers of evidence where we strip away the complexity and build an understanding on the fundamental constraints that physics provides us. And it's an interesting problem to think it's just about Earth, but all of these types of approaches can be applied to any other planet. And that's sort of the beauty of, and sort of the applicability of physics can go beyond just one instance. So I think that's, probably the best way I could summarize it for now.
And I want to dive a little bit into your own backstory. What did you think you were going to be when you were growing up? Or what did you want to be?
I think similar to, as I was alluding to in my discussion of my career trajectory, I don't think ever said, I want to be a professor. And when I think back to what I did say in response to that question, I don't think there was any profound, enlightened, I want to be a doctor, I want to be a lawyer, I want to be a mechanic. I don't know if it's just I don't remember, but I certainly remember going through school and navigating things I liked and didn't like. And I think that was maybe more the aspect of my personality where I wasn't really sure. But I was very open to experiencing different things. And that, I think, has been one of my most valuable attributes that I've learned by doing. And, obviously with the support of my family, one of the most important people that kind of enabled that ability to do things and learn if I liked them or not was my mother, who always provided opportunity. So, whether it was enrolling in, an engineering camp in the summer, or, whether it was, pointing out that earth science was an actual discipline that maybe I should think of, just in these moments, I was clearly not focused on one thing, but having those perturbations, someone to point out something that I could consider was really useful for, I think, kind of narrowing the scope of where I ended up going. So it wasn't a straight line path, but it was a path that was always being course corrected, I think, with a very useful input from outside.
And what were you like as a student? You've mentioned math quite a bit. Did you always excel at math?
No, actually. So high school was a very interesting time for me. At the beginning, I wasn't a super good student. I was more interested in other things. Maybe one could describe it as sowing wild oats or something. It really wasn't until, several years into high school where I think was maybe realizing that the path I was on wasn't really a good path. And thankfully also was taking a course in math with a teacher who was really exceptional. And I can't even really necessarily put into words what it was about her, but somehow, whether in combination of her enthusiasm or just the topic, or just not only showing us that what we could do, but what was beyond what we were doing, and also just, I guess, being able to be good at it, that really was what catalyzed my interest in math in particular, but then ultimately, I think, more in sort of mathematical, physical sciences in general. And I remember a distinct conversation. It's funny how you remember certain things and not others, but where she had been talking with my parents about, what are the opportunities for someone who is interested in math? Because they, as I said, were not at all involved in academia or hadn't taken any advanced degrees. And I remember this teacher kind of recognizing that they wanted some really tangible profession, because engineering was not going to be where I was going to go. It was too practical, I think, not necessarily enough open-endedness. And so she said, actuary or, something this is, the 90s or something. And so I'm always grateful to that teacher too, for sort of, giving my parents the peace of mind to sort of realize that whether it was an actuary or something, that these kind of skills are really valuable, and, that I should be encouraged to pursue, to take it whatever direction I so chose. So a lot of little things, I think, coming together in the end.
What about people that supported you throughout this path? Who would you point to as being some of your key support?
Yeah, so early on, for sure, as I mentioned, my mother in particular, just being there, paying attention, offering opportunities, and also, guidance, help along the way. But then when it got into, the more practical aspects of actually the doing of math or physics or science, then it ultimately became teachers and professors in high school. That one math professor, I don't think I also mentioned, had an advanced degree. I think she had a master's. And that, I don't know, just showing that what was possible and what could be revealed using math beyond what we were learning in the classroom, I think was really, really a foundational thing for me. And then in undergrad, as I mentioned, the sort of being guided toward type of science that I never would have even known existed by professors such as a math professor who had done a little geophysical fluid dynamics, which is the study of rotating stratified fluids like the atmosphere, and saying, hey, you should go over to your science department and, talk with professor there, because, there's a lot of research, that's going on in that area. So that was really important. And then, of course, in my PhD years, it was my PhD advisor. There was nothing I couldn't do there. I was given all the opportunities, to apply for things, to go to summer schools, to go to conferences. I had never experienced anything like that before, to really have the door opened all the way and essentially have the privilege to decide whether I wanted to step through it or not. He was really, really critical. And then setting me up for the next level, pointing me to places which would be, good to go to, pointing me to people, introducing me to people, just putting me out there and allowing me to make those connections, which were, going to be the next step, or would allow me to take the next step in my career. Once I finished my PhD, I had postdoctoral mentors as well, and colleagues today who continue to be a valuable source of information as I, go through the process of teaching and research and being an academic. There's people in my department who I can go and knock on their doors, and I will get very useful and valuable feedback.
And so what would you say are the most fun parts of your job? I think you mentioned earlier in our conversation something about flying planes.
It continues to be a recreational hobby. It's not something that I have brought into the realm of my research, but certainly is a good thing that motivates, I think, the questions and sort of things that I'm interested in doing with science. I mean, science is this beautiful thing where you get to ask questions about the way the world works, in my case in particular, about the factors that shape the Earth's climate today and how, changing carbon dioxide concentrations will shape the climate in the future. And there's no one telling me how to ask the questions or what questions to ask or how to answer them, which of course is potentially a little daunting, but we all are in this together as climate scientists. And of course we collaborate a lot. And so it's just this open-endedness that I just never knew existed, and the gratification of taking a step toward answering some of these questions and, getting that information that could be used, but also, reaching dead ends and realizing that the system is beautiful and complicated. And, we got to ask a different question. It's just, I just can't think of a better job. I just can't think of a better job. And then to top it all off, I get to do that, in my own time with my own colleagues, but also get to train the next generation by working with undergraduate students and graduate students here at the university who are exceptional. Yeah, it's just a really amazing job to have.
What would be your advice to someone who is potentially interested in pursuing academia as a career, and specifically the type of research that you do?
I think, as I've kind of highlighted in my own career, getting the opportunity or applying for research experiences is the really critical advice that I would pass along to someone interested in entering the area of climate science or just research in general. We don't have undergraduate degrees in climate science, so a lot of people come at it from different angles, whether it's physical science or mathematical science or just chemistry, or even, people who are just doing biology or more general kind of undergraduate degrees. The only way you can really know if you like something or not, in particular what it means to do science, and there's different types of science even after you've agreed that you're interested in science, is to do it, is to try it. So the good news today is that there's a lot more opportunities even than in my day to get involved. So I can give you a few examples of those. One, for example, at the university, I continually train undergraduate students in my research just by being a professor and teaching a class. And so I always encourage students to reach out to professors. If they are interested in a research opportunity, reach out and ask what opportunities exist. Do you have an opportunity in your lab? You have to, take that first step. So that's internally within the University of Chicago. Reach out to your professors, see if they're looking for a research intern. And then another thing that opportunities that are more broadly outside the university are research experiences connected to the National Science Foundation, the so-called REUs. There's also research experiences associated with the National Oceanic and Atmospheric Administration. And there are research experiences that I've had students come through from Leadership Alliance, which is a program that is increasing the participation of underrepresented minorities in science. And just to be clear, all of these opportunities are paid. So that's the other amazing thing, I guess, about science, is that you are being paid to do this. Of course, that should always be clarified in advance, but any kind of external fellowship or any kind of external research opportunity is paid. But you can always, be sure about that in any internal situation by asking. So I guess that's my main advice. On the research side, of course, taking classes is another important way of learning about a subject area. And one nice thing about our department, several of us are doing what we call flipped classrooms, where students get a lot more hands-on experience with the science and solving problems in the classroom. And the lecture component is sort of something they do in advance, watch a video, read some notes. And I think that's been a good way for the students to get a hands-on sense of what are the kinds of problems that we're solving, what are the kinds of tools that we're bringing to bear to solve these problems. And that's, I think, how it's been a good streamlined approach to get students involved in research, because they can see what sort of things that we're doing through the coursework that they are engaged in.
I've been speaking with Professor Tiffany Shaw. Professor, thank you for your time. And course takers, if you enjoyed listening to today's interview, please check out the other ones. Leave us a comment, subscribe, follow, and share this episode with your friends and family. You can find out more about the University of Chicago through uchicago.edu or the university's campus in Hong Kong through uchicago.hk. Stay tuned for more, and thanks for listening.